Good evening, good day, and good morning, everyone, depending on where you're right now. And welcome to our 11th Grammarly AI-NLP Club. So it's kind of anniversary, so it's first club after the dozen. My name is Victor. I'm engineering manager at Grammarly and leading applied research and ML teams here in Kyiv. And I'm really pleased to moderate tonight's meetup. Just to reiterate, so the main goals of this club, of Grammarly AI-NLP clubs, to bring together leaders in the field and specialists interested in AI, machine learning, and in NLP in particular. So a big shout out to Maksym for joining us today. And definitely to contribute to the development of the AI community in Ukraine. Just to be sure that we are developing this community in a well manner and effectively and efficiently, please keep in mind that we have a networking event after the meetup, and they're intended as an opportunity for you to connect with the new and interesting people. So we're inviting you to a Zoom call to chat in an informal atmosphere after the talk. You'll have a chance to chat with Maksym and with the Grammarly team. So the link to this call, to the networking call, you can find in your registration confirmation, and definitely we'll post it into Zoom chat during this talk. So everyone, you're very welcome and encouraged to talk to each other, to Maksym and to Grammarly team as well. So during this talk, we'll have a few breaks for our Q&A sessions. Maksym will make pauses and answer on these questions. Please submit your questions via Q&A toolbox in Zoom, so we can actually see them and answer on all of them. And definitely, so there is an opportunity to ask Maksym about anything, even beyond his main talk during the networking session. Don't miss your chance. So now let's get to the main part of today's meetup, and I'm thrilled to introduce Maksym Andriushchenko. Maksym is a second-year PhD student in computer science at EPFL, a research institute and university in Lausanne, Switzerland, that specializes in natural science and engineering. He obtained Master Science from Charlotte University in Germany, and his research mainly focused on how to make machine learning algorithms adversarially robust and improve their reliability. Maksym has published several papers at major machine learning and computer vision conferences, and now he's excited to give a talk at this club. So please welcome in joining Maksym together with me. Hey, Maksym, the stage is yours.
Okay, thanks a lot. That was a very nice introduction. So, okay, let's get started. So, so the topic of this presentation is essentially it's based on our recent paper, which is called On the Stability of Fine-Tuning BERT, Misconceptions, Explanations, and Strong Baselines. So basically, this is joint work with Mariusz Mosbach, who is actually the first author, and I'm the second, and he's, I believe, present now in the audience, and also Dietrich Klakov, who is the supervisor of Mariusz from Charlotte University, where I did my master's. Okay, so this paper is published at ICLR of this year, so it's quite recent work, and okay, so it has 23 citations, so I just wanted to highlight that it's kind of, okay, so people are using this work, people kind of the ideas in this work that they are kind of, let's say, quite relevant in like in the research community, and therefore I think they can also be relevant like for practitioners, let's say for maybe for companies like Grammarly and the audience around it. Okay, so okay, as it was mentioned, so I'm a second-year PhD student at the Swiss Federal Institute of Technology, which is also known as EPFL, and I'm also scientific advisor at Scrum Meister, which is a startup which develops an AI-powered assistant for Jira. So there's a bit of NLP involved there, and so we are looking into ways how to use the ideas from research also for startups. Okay, so let's get started from the introduction to this paper and some background knowledge. But yeah, as it was mentioned, so feel free to submit your questions, and after each section, and I think we'll have four or five sections, I'll be happy to answer your questions. So let's make it as interactive as possible. Okay, so quick background knowledge about transfer learning. So essentially, transfer learning is the kind of the paradigm that we are going to discuss today during this talk, right? So this is the main kind of workhorse for many domains now, especially like computer vision and NLP. And there's a famous quote from Andriushchenko that transfer learning will be the next driver of ML success. So it was said back in 2016, and I think these words were very true. So so I think now it's a very important paradigm to know about. Okay, and we consider basically in this paper a large neural network. So we assume that we have some, okay, so the architectural details do not matter, but let's say we have a large black box such as this BERT model, which stands for bidirectional encoder representations from transformers, where transformers is a particular architecture. But again, it's not too important for in the context of this talk how exactly it works inside. Maybe just to mention the overall scheme, like what is the input and output to this black box. Essentially, this is the overall scheme. So this figure is taken from the original BERT paper. Essentially, so we have a two-stage process. So on the first stage, so the first stage is called pre-training, where we take this large neural network, this large bidirectional encoder network, and we feed unlabeled data, which are sequences of words. So we can just take any data essentially from the internet, let's say Wikipedia, or even larger data sets. And what we do is we mask some tokens in the essentially in the inputs, and we try to predict the missing words, right? So or missing tokens in general. And this kind of very simple task, so it has kind of a supervised flavor in the sense that we always have a classification task on each time step. So for each omitted element of the sequence, we have to predict essentially the missing word. But the interesting part here is that we can use actually unlabeled data, and we have a lot of unlabeled data on the internet, right? So it's kind of very easy to get data for training, and therefore we can train models on super large data sets. Okay, so this is pre-training. So it's just what is known as language modeling task or masked language modeling task. So we just want to be able to predict well missing words. Okay, and there's a second stage, which is called fine-tuning, where we take this very large model and we fine-tune it. Okay, fine-tune means we train it further. So we take the initialization from the pre-trained weights of this BERT model, and we train it a bit further on some downstream dataset. And the remarkable property is that this downstream dataset can be much, much smaller, right? So if we train, let's say, on I don't know, millions of sentences, then we can take essentially like a downstream data set, which consists of maybe, I don't know, hundreds of examples or maybe thousands of examples, right? And we actually can transfer knowledge from the pre-training task to the target task, right? And therefore it's called transfer learning because we transfer knowledge from one task to another. Okay, and the architecture is essentially the same at the fine-tuning stage, but it can differ a bit based on the task. Sometimes we are interested in classification, and there is some specific classification token that is built in this model, so we can use it in order to kind of extract predictions for the fine-tuning task. Okay, that was a super brief overview of what's going on in this paper and what is the overall paradigm that we consider. So, and maybe just some small historical facts. So transfer learning has been very popular on ImageNet first, so maybe starting from 2014 or 15, but actually it took a while for NLP to catch up with the progress on ImageNet. And if you're curious, then there's a very nice overview from Sebastian Ruder, who is a researcher at DeepMind, I believe, where essentially he covers different approaches for this pre-training fine-tuning paradigm. So it basically dates back to July 2018, and there have been already successful architectures, successful approaches for this. And just a historical note, BERT, which became even more popular, came a bit slightly later, so November 2018. So actually it was not so a long time ago, which is actually quite important fact, because it also means that there can be some blind spots which we don't yet understand, and it would be nice to understand them better in order to kind of to make progress in this area. Okay, so before we like really start from the content of the paper itself, so maybe what to expect from this talk. So I'm more on the machine learning side, so I'm not a computational linguist. So for me, like the general problem is essentially transfer learning, right? So it is so whatever I will say will be applied to NLP, but conclusions are likely to be quite general, and perhaps the same should also hold for other domains such as images or speech or maybe something else. Okay, so what we are interested is we're interested in developing a better understanding of some algorithmic properties, right? So we are not really so from our perspective, we're not really interested in some linguistic properties of these models, right? So, and there are a lot of works that try to interpret what's going on, like let's say, what is encoded in the latent space of this BERT-based models, right? And I think it even has a name like BERTology, when people try to really understand what's going on inside these models, because they are very large and they are black boxes, and it would be very beneficial to better understand how exactly they work, right? So so here we focus on algorithmic properties, and such as primarily fine-tuning stability. Okay, I will tell you later what precisely it means. Okay, and you'll see that it's fruitful to consider the problem from the optimization point of view. So optimization in the sense of mathematical optimization. So when you try to optimize some function, and you are using essentially a variant of gradient descent for it, and it's a bit tricky part because we don't have any guarantees on the performance of gradient descent for non-convex functions such as the loss of a neural network. But we'll come to this in more detail. Okay, so let's start from the motivation of the paper. So so we know that transfer learning is great. So Andrew and G said that is great. So it's kind of quite exciting already, but it should be better understood, right? So in particular, I think our explorations in this area started from this tweet, which dates back to February 2020. There is a researcher, JC Dodge, from I think he was a PhD student at Carnegie Mellon University, and they released a paper that's called Fine-Tuning Pre-Trained Language Models, Weight Initializations, Data Orders, and Early Stopping. Okay, so what they claimed is that they found surprisingly large variance just from random seeds when fine-tuning BERT. Both weight inits and the order of the training data have big impact. So essentially, it just means that, so you fine-tune your large language model, right? And your performance is not stable over random seeds, right? So, so what are the consequences of this fact? First of all, it's an important issue for reproducibility in the NLP research. And second, maybe even more importantly, is that we don't really understand what's going on, right? And this kind of motivated us to look more into this, right? Because we are kind of like both me and the first author Marius, we are like PhD students, right, in academia, like in universities, right? So we are really driven by this idea of understanding something, right? So if something is unclear and nobody has an idea what's going on, this is kind of an exciting opportunity to really find something out. Okay. So let's start from this paper of this JC Dodge and collaborators. So what was their main claims, right? So if we try to look beyond their tweets, but actually we open their paper. So what they show in their paper is the following. So there are some data sets such as MRPC, RT, and COLA. It doesn't really matter what are these tasks are. So just some NLP tasks on which this transfer learning paradigm was actually very successful. And basically, they noticed that, okay, there's actually a large set of such data sets, which is known as glue benchmark, and there's also super glue benchmark. So there are some standard benchmarks for this. And there are some data sets, like not all, but some data sets like this MRPC, RT, and COLA, which have unstable fine-tuning performance, right? So in particular, on these heat maps, they show the following. So basically on the x-axis, they have data order, okay, random seeds for the data order. So which means that when we run stochastic gradient descent in order to fine-tune our model, essentially there is a different order of the batches that you input in your model, and it affects, so it's just one source of randomness, and another source of randomness comes from the weight initialization. Okay, so weight initialization, okay, this may be just important to understand, right? So we take the network from the initialization that was actually obtained from pre-training, but we may need to initialize from scratch, from some random initialization, the top layer, let's say the classification layer, if our task is classification. Okay, so there are two sources of randomness, and essentially each cell represents the performance in terms of the target metric. So for MRPC, this accuracy, so some, I think it's just the average between accuracy and the F1 score. For RT, just simply accuracy, and for COLA is something known as Matthew correlation coefficient. Again, not too important what it means, but just some performance metric. And essentially, it can be seen that the distribution of the performance is quite bimodal, right? So which means, for example, if you take MRPC, so either the cells are, let's say, close to yellow or green, or they are dark, right? So like most of them. So if we are to plot the distribution, it would be quite bimodal, right? So it kind of already suggests that like either we fail almost completely or we succeed, right? So, and this will be important observation later on. Okay, and and just to be clear, so kind of roughly the same behavior is observed on all these three data sets, right? And in particular, the frequency of the failures is different for every data set. For example, on COLA, it is already quite stable, so we don't have too many dark cells here, but still it is concerning that sometimes fine-tuning can fail. Okay, so the main question here is, why is fine-tuning prone to failures, and how can we improve its stability? Okay, so there was another work, Lee et al., which was published at ICLR 2020 of last year. So basically, what the paper is called Mix Out, Effective Regularization to Fine-Tune Large-Scale Pre-trained Language Models. So they propose Mix Out, which is a variant of Dropout adapted to the transfer learning setting. Okay, I will not explain in detail what is this, right? Just, let's say, some regularization method that is inspired by Dropout. And what they show, so basically on these box plots, they have essentially, again, two data sets out of three previous ones, right? So it's RT, again, RT, and MRPC. And so basically they compare several methods. So Devlin is the original BERT paper. Then there is some other method, and their method plus other method, right? So they show that their approach does improve, let's say, the average, right? So basically on the y-axis, we have the development score in terms of either accuracy or other performance metric. And they show that essentially the distribution becomes better, right? Especially if they combine their method with some existing method. but there are still some failed runs where fine-tuning fails completely. Okay, and the same also can be observed on the second data set as well. So mix out helps, but there are still failed runs, and we thought that there is some more room for understanding about what's going on. Okay, so now our paper. So okay, so maybe just to be clear about some definitions, so that we are really precise about what we are talking about. So first of all, what is fine-tuning stability, right? So we have this in the title of the paper, and we have it everywhere, right? But we need to somehow define it precisely, right? So we define it as the variance of the performance measured in some target metric, let's say accuracy, right? So if we come back one slide before, right? So we have, when we run the method over different random seeds, we get some distribution of the final performances of models, right? So these are all like every point corresponds to a different fine-tuned model. And so we're dealing with the whole distribution, right? And how can we characterize the spread of this distribution? One obvious and natural metric is standard deviation or variance, right? So this is what we really mean by fine-tuning stability. So we define it as the variance of this distribution. And second, what is failed fine-tuning run? It is a run if its accuracy or other performance metric after fine-tuning is less or equal than that of a majority classifier. Right? So majority classifier means that we always predict, okay, so we are in the classification setting, and we always predict the majority class, right? So let's say if you have 90% of cats and 10% of dogs, then trivial performance will be 90%. Okay, so here we are not in the image recognition setting, we are in NLP, so there will be no cats and dogs, but I think the idea should be clear. Okay, so the data sets that we consider are essentially 4 data sets. So RT, MRPC, and COLA are data sets that were already mentioned before. And there is also QNLI data set, which I think we didn't really want to include, but then reviewers say that we should do it. So, okay, so we did it, but I think I will not focus too much on this data set. But I think what is really important here for the first 3 data sets, right? So like the previous literature observed that there is fine-tuning instability on these 3 data sets, RT, MRPC, and COLA. And what is common to all 3 of them is the size of the training data, right? So it's, let's say, 2,500 examples, 3,600 examples, 8,500 examples. And this kind of led to the idea that maybe it has this fine-tuning instability has something to do with essentially the size of the training data, right? Okay. And our contributions, just to quickly summarize what to expect. So we provide an understanding of the reasons behind this fine-tuning instability. Then we propose a new simple fine-tuning baseline based on our analysis. And these are the results of this fine-tuning baseline. So essentially, so we have this 3 data sets which were observed to be problematic, and we compare our baseline method with the methods of Devlin et al., which is the original BERT, Lee et al., which is the ICLR 20 paper that proposed this mix-out regularization. And essentially, we observed that our distribution is more stable, so it has less variance. So fine-tuning is more stable with our method, and there are no fail runs on either of these 3 datasets. Okay. Okay, so this is the end of the first section, and okay, if you have some questions, then it's a good time to ask them in the chat. And I think I see one question from Maksym. So okay, you say that it's very beneficial to understand of how parts of this black box work. Is there any examples when it was beneficial? Yeah, so I think it's very interesting area. to understand what is encoded in a neural network, and it is okay. So I think it's equally useful both in NLP and in let's say in image recognition and in speech recognition and so on, right? So I think it's I think if we want to improve some system, right, we first need to understand when it fails, right? So for example, if you have a BERT model, right? So I think when the researchers at Google first trained this super large bidirectional transformer, they had no idea what is encoded inside, right? And okay, so they made, let's say, this kind of, let's say, relatively giant leap forward with this model, right? But then the next question is, okay, we have this nice model, BERT, and how to improve it, right? And you need some ideas how to improve it. And one natural way how to find this room for improvement is to try to interpret your model, right? So maybe there's some linguistic knowledge that is okay already encoded in the model, which is very good, but maybe something is missing, and therefore one can maybe use some other data set and somehow complement the training procedures so that this knowledge is incorporated and the performance of the model is improved, right? So I think it's really, I think there are many examples and there are many papers that try to understand something, how the model is working, and then propose a method how to improve some deficiencies of this model, and they get better results. Yeah, but I'm not sure if I can tell on top of my head some particular papers of this kind, but I'm sure there are many of them. Okay. Okay, so I think if I answer a question in this form, okay, done. Okay, I hope it answered your question. Okay, the next question is from another Maksym. Have you compared your method with reformer architecture advantages? Oh, I think reformer actually came later. So I think okay, so our paper, the first version of our paper is dates back to May or June of the last year. I think at that point, reformer was not around. So basically, in the paper, we consider fine-tuning BERT, Albert, and maybe some. I think it's RoBERTa. So we took state-of-the-art models, let's say, which were state-of-the-art at May 2020, and we just evaluated them. Okay. Do you have a box plot for the fourth data set? For the fourth data set, that's a good question. Maybe we have it in the appendix. I think it's possible that we have it in the appendix, I think. But I'm not sure. Okay, let me think. Yeah, I think we have it in the appendix, and roughly the picture is that. Okay, so maybe I can show you again this table of data sets. So basically, this fourth data set QNLI, it has more than 100,000 examples, and we observed that actually, even if you use the default training scheme, it already leads to stable fine tuning on this data set. Okay, what is the fastest way to detect failing run in terms of GPU usage and time? Okay, that's a great question. So basically, the standard standard fine-tuning procedure is to fine-tune the model for 3 epochs, right? So one way is to basically do this fine-tuning and see whether it failed or not, but actually you can even detect it a bit earlier. So I think, if I remember correctly, this paper, Dodge et al., they also proposed some method to identify failed runs early on. So I think if you're interested in this, then it makes sense to check this paper where they propose some early stopping scheme, in a sense that you completely stop the run if it's not promising, if you see that it kind of got stuck already very early during fine-tuning. Okay, another question from Vitaly. Hello, results of your method for dataset number 4. Does this non-stability shift persist for live datasets? Okay, actually, okay. So I think this was already answered. So basically, there was no instability on the 4th dataset. Okay. Question from Anastasia: fine-tuning stability is variance across time epochs or datasets within a single fine-tuned model or across different fine-tuning methods. Okay, so basically, if we go, let's say, to the box plots, to these box plots, right? So we get one data point after the whole fine-tuning, right? So we take BERT, we fine-tune it, and we measure the performance at the end of fine-tuning, right? So, and then we get single number, and then we repeat this procedure over the randomness of the algorithm, essentially over different random seeds, right? So, and then every random seed leads to one value of accuracy or some other performance metric, right? So it is not stability taken over time or over epochs, but really after the whole training for some particular method. Okay, and the last question from Zvimka: is there a correlation between fine-tuning dataset size and fine-tuning stability? Yes, there is exactly a correlation, but this is just a correlation, as we will show later on, and it's not very so it's not it's just a correlation, right? So it's not cause, it's not causal, it's not like cause and effect. Okay. Can you tell more about optimizer used? Any hacks with its parameters? Okay, this is, we will tell about all the hacks that have to be done to the optimizer, and this will be essentially our baseline that we propose. Okay, wonderful. Thanks a lot for being super active. I hope I still have enough time to finish everything in time. Okay, so section 2 is about investigating previous hypotheses for fine-tuning instability, and there were actually 2 of them. So first is catastrophic forgetting, that somehow during fine-tuning you encounter this catastrophic forgetting issue, and essentially the work of Lee et al., this ICLR 20 paper, they kind of came up with a regularization method, mix out, which was which they wanted to use to prevent this catastrophic forgetting. And the second is exactly small training dataset size, which was pointed out by Dodge et al., and I think even by some earlier works. We show by careful experiments that none of these hypotheses actually can accurately explain this fine-tuning instability. Like, okay, so basically, okay, I'd like to be careful here, right? So indeed, these 2 things, they do correlate with fine-tuning instability, but both of them are not very helpful to really understand what's going on and to kind of to go forward and really to improve the performance of the stability of fine-tuning. Yeah, so the 2 reasons are rather connected to optimization difficulties during fine-tuning, which I will cover in the next section. Okay, so let's start from this first hypothesis about catastrophic forgetting. So, okay, so Lee et al. Motivate their method to, they aim to prevent this catastrophic forgetting issue, right? But we wanted to really understand how can we really develop some nice experimental setting where we would be able to test how this catastrophic forgetting happens in fine-tuning BERT. Okay, so this is the first hypothesis, and so we investigate the the language modeling performance of the BERT model, right? So we take the BERT model, we fine-tune it on some data set, and we also measure how well the performance, on the original task, which is language modeling or masked language modeling, how well it preserves after fine-tuning. And we check this both for failed and successful fine-tuning runs. Okay, and what we do is the following experiment. We take essentially 2 snapshots of the models. So first is before fine-tuning, and second is after, and then we replace top K layers of the fine-tuned model with the original BERT layers. Okay, and this is what's going on. So the first plot is perplexity of failed models, right? So, okay, so the lower, the better. And essentially, okay, so on the x-axis, we have the top, the number of layers replaced. And on the y-axis, we have this masked language modeling perplexity. And we see that, okay, that essentially, just to be clear, right? So if we substitute all 24 layers, right, then we just get back to the original BERT model, right, which has quite good performance on the language modeling task, right? And if we don't substitute anything, then we are just back to the fine-tuned model, and we also are interested in the performance in between. So if we take a look onto a failed model, then we can see that actually this catastrophic forgetting does occur, but in quite interesting way. So the overall picture is quite nuanced. So in the sense that catastrophic forgetting does happen, but it happens only in the top layers of the network, right? Okay, and there are 3 curves here because we took 3 models over 3 different random seeds to see the variation over the random seeds. Although all these 3 models here are failed, and all 3 models here are actually successful. Okay, so basically what's going on here is that, let's say, especially for these two models, for these 2 random seeds, we see that basically if you substitute, let's say, top 10 layers, then we can recover roughly the original language modeling performance, right? So this catastrophic catastrophic forgetting happens in the top layers of the network, right? And at the same time, for successful models, we can see that y-axis is of much smaller scale. So it goes from 9 to 27 instead of up to 10 to the power of 8. So basically, for successful models, so the successful models do retain to some degree the original language modeling performance, right? However, if you really check the definition of catastrophic forgetting, it usually means that that basically a new task is learned, right? So it's like a new task is learned and the previous task is forgotten, right? But this is actually not the case here for failed models, right? Because failed models are not, as we observed them later on, right? Okay, so it's not reflected on this plot, but we just checked it. They do not have any good performance on the target data set. So kind of a new task was not learned and the old task was forgotten. So it's actually a bit different from how people use this term catastrophic forgetting, and essentially which is actually more relevant in the multitask learning setting, where we really want to retain the performance on the original task and also be good at some other downstream task, right? So, but this is not really, so when we fine-tune BERT, it's not really multitask learning. So it's really transfer learning setup, which is different. And there is probably not so, I mean, just probably a wrong language to talk about catastrophic forgetting for in the transfer learning setting, because we don't really there are no reasons why we would want to preserve the original language modeling performance unless our target task requires to do so. Okay, so kind of the overall message is that catastrophic forgetting does happen, but it happens on the top layers, and actually it's not the right language, not very insightful language to talk about this particular problem. Okay. The second hypothesis is probably even more interesting. It's about the size of the training data. And okay, before starting to describe this, can I ask Victor about should I end at 6:20 or is it fine to end at 6:30?
Let's continue. So I think we're good to continue to 6 or 7:30 based on where we are. So
yeah.
15 minutes more. Probably we want to push all the questions to the end of the presentation.
Okay. This sounds good. Okay, 15 more minutes. I think that should be enough. Okay. Yeah. So about the size of the training data sets. So here is the following experiment. So what we do here, we have 3 data sets. Okay. Now we have QNLI as well. Okay, actually, we do have QNLI here. Okay, it's not only in the appendix, it's also on the slides. That's very good. So essentially, if we fine-tune QNLI using 3 epochs with the full training set size, then we get very stable fine-tuning performance. So this just to answer the previous questions with some data. Okay, and actually the experiment that we did was to downsample, like let's say, okay, so essentially fine-tuning is stable on this data set, and what happens if you just subsample the training data? So instead of 100,000 examples, right, the full training set, we have 1,000, right, which is kind of roughly on the order of magnitude of what MRPC and COLA have. And essentially we observed that if you downsample the number of training data, then we have again this instability problem, right? So it might imply that, okay, that this is really the reason, right? So really the training set size, right? But okay, actually it's just correlation, because what we also tried to do then, we tried to increase the number of epochs, right? So essentially we train, instead of 3 epochs, we train for let's say 300 epochs, right? So we train much longer. And we see that if you train much longer, then there's no problem anymore, and we are able to recover this like a very high level of stability of the on this data set. Although the average performance is a bit worse, but this is because we have less training data to generalize well, right? But the stability can be actually recovered even with 1,000 data points, right? And the same observation holds for all these 3 data sets, right? So indeed, the training set size matters, but actually it's not the primary reason for the observed instability, right? So it's just a correlation, but it's not, there is no causal relationship, right? So what is crucial is rather really the number of training iterations, which is actually linked to the dataset size, right? Because if you think about it, what Devlin et al. Said in their BERT paper is that we should, like everybody should fine-tune for 3 epochs, but 3 epochs for a small data set is much less iterations than 3 epochs for a large data set, right? So kind of a short story is that it would be better if one would fix the number of iterations and not the number of epochs, because there is a dependency on the data set size. Okay, so the conclusion is that the role of training data size per se is orthogonal to fine-tuning stability, and what matters is rather the number of training iterations. Okay, so this is the end of section 2. Okay, we agreed to postpone the questions to the end to make it a bit faster. And section 3 is about disentangling optimization and generalization in fine-tuning instability. Okay, so what really causes fine-tuning instability? So we tried to look into this question in more detail, and again we'll be doing it from the optimization perspective, since we observed that the number of iterations matters, right? So we want to understand this a bit deeper. Okay, so the key observation is that failed fine-tuning runs actually don't train at all. Okay, so what it means precisely is, okay, so here is essentially the plot over iterations for successful runs and for failed runs. And we see that for successful runs, okay, so on one axis, on the first y-axis, we have accuracy, the blue curve, and the red curve corresponds to training loss. So we see that for a successful run, the training loss nicely goes down, and this is consistent over different seeds, right? So we have this shaded area corresponds to the fact that we were running this over many successful random seeds, and here we did the same, but for failed random seeds. The training loss nicely goes down for successful runs, and test set accuracy nicely grows. So everything is good here. But for failed runs, we observed that the loss, which was around 0.7 in the beginning, it just stays constant, right? So the model does not train at all. So it's not like it first went down and then something happened, right? So it really, the model really does not train, right? And accuracy also stays at 50%, basically at the trivial value. Okay, moreover, so we tried also to look at and visualize the loss surfaces. So essentially what it means is, okay, so here is for 3 data sets, we plotted the loss surface, so essentially a 2-dimensional slice of the loss surface in the weight space of the neural network. right? So just to be clear, the weight space is a very high dimensional space. So it has millions or even billions of parameters, and we're just projecting everything down to a two-dimensional space. So apparently it's a lossy compression, but still, the main message here is that that essentially we start at this point 0, 0, and here this point theta s corresponds to this to a successful fine-tuning run, and theta f to a failed fine-tuning run, and we can see that we started at some, let's say, relatively high loss value, which is around 0.75 or something like this. And if we fail, then we converge to some valley. So we go far away from the minimum. Okay, so this is a good area with a small value of the training loss. And when we fail, we instead go to some valley where we just get stuck with, with roughly the same loss value as in the beginning, or maybe slightly smaller, but not substantially smaller, right? And what is really remarkable, probably, that the same consistency was observed over all the data sets that that we had, that basically we converge to this suboptimal valley where we just get stuck, right? So this is kind of probably not too surprising. This may happen because we are in the non-convex optimization setting, so we don't have any guarantees on the optimization of our function, but essentially, yeah, so it matters how you optimize your function and how you select hyperparameters for it. Okay, and moreover, there's also an observation about vanishing gradients, that essentially after the model got stuck, so for a failed run, we can see that the gradient norm is, like, over different layers, is actually much smaller than for successful runs, right? So we also have, so we get stuck with in this valley with very small gradients, so we essentially do not move anywhere anymore. Okay, how to fix this optimization instability? So it can be avoided by carefully choosing the step size, right? So basically, we have we have tried to do a grid search over different values of the step size, and essentially, just to briefly summarize the message, so it really matters to select the right step size, which can lead to much better fine-tuning stability. Or alternatively, there's also a very important thing in the Adam optimizer. There is such thing that's called bias correction. Okay, maybe I should tell that okay, that all, like, this fine tuning is done with a variant of stochastic gradient descent, and the precise method is known as Adam, which is just a fancy version of stochastic gradient descent. And in the original Adam paper, they have this bias correction term, which essentially multiplies the learning rate by some factor. And this factor, if we plot it over iterations, then it looks like this. So it's just some multiplicative factor, which roughly increases from 0.2 to 1. So essentially, it makes the learning rate smaller in the first iterations, right? So again, it's linked to a step size selection and to the fact that it has to be carefully selected. And actually, this bias correction, which was okay, so this bias correction term was actually removed accidentally from the implementation of BERT. And actually, if you just enable it, it already would help you a lot to improve the fine-tuning instability. Okay, so, and there's also some role of generalization. So essentially, the remaining variance in the performance can be explained by different generalization properties. What is meant here is that essentially, if we take a look, for example, on this plot, right? So here we plot the development set accuracy over training iterations, and we plot 10 successful runs, and we can see that this 10 different models, although they're all successful, they converge to slightly different value of the accuracy, and so there's still some variance because of generalization, but it is much less than the variance that's coming from optimization difficulties, right? And on this plot, we took just really all our models that we produced for this paper, which was something like 450 models, I think, and we plotted the dependency on the training loss, between training loss and accuracy, and we observed that essentially even if you train down to zero loss on the downstream task, you actually do not really overfit, and you still have a bit of variance. But again, this variance is much smaller than the variance that's coming from the optimization difficulties. Okay, this is the end of section 3, and again, the questions will be postponed until the end. So I think maybe like 3 minutes, and then I'm done with the presentation. Okay, so the section 4 is called Simple but Hard to Beat Baseline for Fine-Tuning BERT. So this basically, there are 2 steps in this simple baseline, right? Okay, so why simplicity is important, right? Because some people are proposing some crazy and complicated methods, right, to against this instability, right? Something like this mix out or some other regularization methods, right? But actually, I think simplicity here is really a good thing, because we can pin down the problem to its cause and do minimal modifications to the algorithm and get back the desired level of fine-tuning stability, right? Okay, so the first step is to use smaller learning rates with bias correction to avoid this vanishing gradients early in training. So essentially, the message here is that the initial steps that you do in your fine-tuning optimization process are really crucial. And second is to increase the number of iterations and train to almost zero training loss. Okay, since we observed that even if you have zero training loss or 10 to the -5, you do not really overfit. So you can train as long as you want, at least on this data sets that you considered. Maybe there are some adversarial data sets that on which you do observe overfitting, but we did not encounter that. Okay, so the results of the proposed baseline methods are essentially, this is the same picture as I've already shown, but maybe just to briefly summarize. So we compare our method to the original BERT paper, which is Devlin et al., and also to this mix-out approach of Lee et al. On these 3 data sets, and we observe that fine-tuning with our simple baseline leads to more stable performance, in the sense that the variance of this distribution is smaller on all 3 data sets. And there are, importantly, there are no failed runs for our scheme, unlike for the method of Lee et al. And there is, much smaller standard deviation, as I just mentioned. Okay, and then if we take a look onto the same essentially results, but in a tabular format. So basically, okay, first of all, if we quantify the standard deviation, right? So if you really want to report some number and not just judge according to the picture. So let's say the standard deviation for Devlin et al. Method was 4.5 on RT, and we can reduce it almost 2 times more. And on MRPC, it's even, I don't know, 5 times more stable fine-tuning, and on COLA, it's even more than that. And we also put a star here, which denotes that the results were validated with a statistical test. So just to be sure that we are rigorous enough and our claims are validated by a statistical test, and much higher mean value as well, right? So on RT, it's higher on MRPC, and also it's higher on COLA, which is basically mainly due to the lack of failed runs, right? Because if you take the average of this distribution, and if it's bimodal, like there are some failed runs, then they bias the mean value a lot. Okay, and finally, some conclusions and remarks. So maybe just a small summary that existing explanations for fine-tuning stability were not really accurate, and instead instability can be explained primarily by optimization issues. And what is probably important is that the hyperparameters, such as bias correction and the learning rate for fine-tuning, they need not be the same as for pre-training, right? So ideally, you need to do really a grid search, so some search for hyperparameters for fine-tuning. As for example, this bias correction term was completely removed by the authors of the BERT paper, just because they observed that it doesn't really matter for pre-training, but at the same time, it does matter for some data sets during fine-tuning. And we propose this strong and simple baseline. And it does not really lead to significant computational overhead because it is mostly important to apply it on these small data sets, right? So essentially, some overhead may come from the fact that we are training for longer time, but this is not really a problem because the data sets are small anyway. And there's also just a fun fact that there was also concurrent work also at ICLR 2021 from Cornell University, which is called Revisiting Few Sample BERT Fine-Tuning, with essentially very similar conclusions about the role of bias correction, of Adam, and so on. So it's really interesting that and like our papers were posted on arXiv like within, I think, 1 or 2 days difference. So yeah, it's just nice when like, let's say several research groups validate the conclusions of each other independently. Okay, so the final slide. So I want to thank my co-authors for this productive collaboration. So it's Mariusz Mosbach, who was the first author of this work, and Professor Dietrich Klakov, who is his PhD advisor. And finally, the code for our method is available online. So in case you're curious, you can find it. And yeah, thank you for your attention. In case you have any questions, I would be happy to answer, or also don't hesitate to drop an email. So yeah, thanks a lot for the attention.
Thank you very much, Maksym. That was really great talk. I think like we can like easily afford another 5 to 10 minutes to answer all the questions to be sure that we address all of them. Or I can see 3 in chats. So
okay. Okay, so the first question is yeah, from Nadia. Is bias correction the same issue which was identified in Adam W? Okay, so I think Adam W is a code name for what Devlin et al. Used, right? So in the original BERT paper, so I think it's really like Adam without bias correction. And I think somebody, okay, probably it was identified. Okay, I'm not sure where exactly it was identified, right? I mean, in the sense that, okay, it was identified in our paper. It was also identified, okay, just if I come back in this paper, Zhang et al., and it was, I think it was also identified at some point in the issues of the Hugging Face library, I think, and then the Hugging Face library at some point fixed it, and suddenly the fine-tuning on this data set became dependent on the particular version of the library that you're using. So there was some confusion about this for sure, and I think it's kind of important to have this important implementation detail, this bias correction, somewhere written down in some research paper where its effect is clearly studied and clearly understood. Okay, the next question is from Olha. For loss surface plots, do we slice to random weight dimensions or the most important chosen via something like eigenvalues analysis dimensions? Okay, this is a great question. And so just to come back to what is meant is, okay, what's meant are these plots, and these directions delta 1 and delta 2, they are chosen at random. So these are really 2 random directions which are sampled, I believe, from Gaussian distribution. So they are just 2 uniformly random directions, and we project everything onto these random directions. So they are not chosen via eigenvalue analysis. Although obviously, I think there are a lot of different choices how you can make this kind of visualizations, and I think it may affect the conclusions to some degree, right? So okay, so we didn't really try anything else. So we just decided, okay, we plot random directions just to be as agnostic as possible to you know, to the final you know, to the shape of these low surfaces, right? So like, okay, somebody in the literature used them successfully, so we just decided, okay, so we just use them, and then we try to interpret what we see, and yeah, so that's what we essentially did. So we went for simplicity here. Okay. Another question from Nadia. Can gradual unfreezing help further? Okay, so gradual unfreezing. Okay, so I'm not exactly sure what is this gradual unfreezing. I remember this paper, this concurrent work of Zhang et al. It was proposed. They proposed some. I think they proposed to reset some top layers of the network. I think, but I think it's not the same as gradual unfreezing. So I think okay. So if I understand correctly, what is gradual unfreezing is that you train maybe in the beginning like the top layer and then top 2 layers, top 3 layers, and so on. So I could assume that this may help, right? But I also think that there is a simpler solution, which is essentially formulated in our simple but hard to beat baseline, which is essentially just doing the hyperparameter search, right? So it's very simple, right? So you don't even need to modify somehow the fine-tuning method, right? You just carefully select the step size, the number of training iterations, and also enable bias correction. So, but I can assume that if you don't do this, but do instead gradient freezing with some successful hyperparameters, you can also achieve stable fine tuning with gradual unfreezing. Okay, Vitaly is asking, did you observe R-Adam work on the variance of the adaptive learning rate and beyond? Okay, if I remember correctly, this paper, they focus on pre-training, right? I may be wrong, but I think they focus on pre-training and not on fine-tuning, right? And I mean, essentially, okay, so essentially what we observed in our paper is that if you just take Adam as it was proposed back in 2015 or 16, that already works, right? So if you just enable bias correction, and then what is remaining is that you just need to do careful hyperparameter search, right? So, okay, so I would say that there is no need for R-Adam or some other complicated, more complicated things that compared to Adam. I mean, okay, so for me, Adam is already quite complicated method because if you look at the algorithm of Adam, it already has like one step, seconds, like first order moments, second order moments, bias correction, you know, like a lot of stuff if you think about it. So I don't know, I would rather go for simplicity. And okay, if it would be possible to use just plain SGD, stochastic gradient descent, then I would even go for that. But I think, and maybe that's impossible. So I'm not sure if this R-Adam is necessary here. Okay, Tatiana is asking, in which range do you suggest to do grid search for the hyperparameters? So, okay, so I think in the appendix of our paper, we have some more details about different hyperparameters that we tried, but essentially the range would be something like, okay, something like for the step size, it's 10 to the minus 5, and then we do search on around that range, right? So I think that's a good range to start from. But then of course, like whenever you do grid search and you see that the best value, let's say in terms of the fine tuning stability, is obtained on the boundary of the grid, then it's always good to extend the grid so to make sure that you don't miss the optimal value of the step size. Okay, then Anna is asking, do you think that presented findings could help with the bit opposite task, disclosure of ambiguity in data and improving its quality? Okay, I need to understand what is disclosure of ambiguity in data and improving its quality. So I think the findings should be quite general, right? So, okay, so as I mentioned in the beginning of the talk, right? So I'm coming from like machine learning background, right? So for me, like whether you fine tune an ImageNet model or you fine tune BERT, so it in principle doesn't make too much difference. So I think even if the domain is completely different, like images versus text, I think it still should not make too much difference, and the same optimization difficulties may arise also for completely different domain. So I would say that if you have different application or different domains, I think these findings can be still useful. Although I'm not aware of any like stability study let's say, of fine-tuning models on ImageNet. Maybe they exist, but I'm not aware of them. So I think it's mostly restricted to these data sets of the GLUE benchmark for NLP. And there's also a question from Zvimka. How about the batch size? Does it influence the stability? Okay, batch size. Okay, so batch size. Okay, let me think. I remember we tried to play a bit with the batch size. Not very sure about the conclusions, but I think, well, okay. First of all, you can't. I think the issue was that you can't easily increase it because I think something like batch size 16 is the maximum that fits onto standard GPU. That is what we had. And you can only decrease it, but I think decreasing the batch size was not very productive because then you introduce even more variance and more randomness in your optimization process because you estimate your gradient for each iteration of mini batch stochastic gradient descent using less samples, which increases the variance, and as a result, I think you may encounter even more instability. So I think so. In the end, we went for fixing the same batch size and just modifying the learning rate. But I can assume maybe that if instead of that you increase the batch size and you have enough memory on your GPU, then maybe it can also help. So it can be another way how to fix this instability, right? I mean, so I'm saying this just based on our experience that really the hyperparameters that concern optimization, that they really do matter a lot, right? And batch size is clearly one of these hyperparameters that are directly linked to the to optimization. So I would assume that it can play quite an important role. Okay, it seems like there are no more questions. Yeah, so I guess then that's it probably for this part of the event. Or
thank you so much, Maksym. That was a great talk.